All right, we're live. So, hey, last time, section 1.5, we looked at some limit theorems, right? What were some of those theorems or proven facts when we don't have to show or prove using epsilon delta? What did we have? We had, first of all, f and g are functions. They're going to be defined on some interval containing a, or except possibly a itself, right? So that's where they're defined. And then we said a couple of different limit theorems. One was the limit of the, as x approaches a, of f plus g, f of x plus g of x, right, is going to be L plus m. So if we have, we also had to assume that the limit as x approaches a of f of x exists and equals L. Limit as x approaches a of g of x exists and equals m. And then for division, m wasn't equal to 0. So we had this one. We also had when you, and what was, how did we say that? What was the lingo for this? We had an abbreviation. Remember? Limit of the sum is the sum limit. So this is how we denote that. We also had the limit of the difference is the difference of the limits, right? I had that. And then we had the limit as x approaches a of f times g evaluated x. What was this? This was L times m. So what was that? The limit of the product is the product of the limit. We had that, right? And then we also had division as long as m wasn't equal to 0. So we can't have that limit approach 0. Then the limit of the quotient is the quotient of the limit, right? And so these are all rules. If we have nice functions defined that actually have a limit as you approach a from both sides, both of these are approaching a. So we had that last time. We kind of went to that, but then we have a few others. First of all, the second one generalizes. Okay, so if I have limit as x approaches a of f sub 1 of x exists and equals L1, limit as x approaches a of f sub 2 of x, so second function, equals L2, all the way down and keep going. So if we have n of these functions, so f sub n of x equals L sub n. All right, then what can we say? Then the limit as x approaches a of f1 times f2 times all the way to times f sub n evaluated at x is going to equal L1 times L2 times, we're going to keep going, times L sub n. So once again, the limit of the product is the product of the limits, but we can have multiple functions. We can have more than two, okay? We can also say that up here, that for number one here, we can say that the limit as x approaches a of f1 plus f2 plus, keep going, 3 dots means that's an ellipse, keep going in the same fashion. What's this going to equal? L1 plus L2 plus all the way to L sub n, right? So the limit of the sum is the sum of the limits when you have multiple ones, more than just two, right? 3 or more. Okay, so same thing here. What if I have differences? It's okay to put differences. What if I have quotient here? Can I put slashes everywhere? Do you think? If I have more than two? Can I put slashes for division? Now you got to be a little bit careful on how you divide, so we don't really want to do that one. All right, so anyway, this is kind of where we ended up. Who stole my eraser? Oh, I did. All right, so we had these limit theorems, then we have a couple more, and then I'm going to go back to the one, so we did some examples of these before. But let's keep going with a couple more theorems. One is, so this is, I think, number 3. If I've got the limit as x approaches a of f of x quantity to the nth power, then this is going to equal the limit as x approaches a of f of x, that quantity to the nth power. In other words, this is going to equal L to the nth power. So how are we going to talk about this one? We're going to say, instead of limit of the power, we already had LP for product, right? So we're going to say the limit of the exponent is the exponent of the limit. The limit of the exponent is the exponent of the limit. So let's look at an example of this. If I have the limit as x approaches 2 of, I don't know, x to the 10th power. Well, how can I rewrite this? By the theorem, proven fact, I can rewrite this as the limit as x approaches 2 of x quantity, this quantity to the 10th power, right? Now there's one limit theorem that we had that I didn't remind you of, and what was that? So I guess bullet point 0. Limit as x approaches a of x, what's that equal? What's x approaches a? No. A, right? So as x approaches 2, what's x approach? 2. So this is 2 to the 10th. And what rule was that? I almost said it. Remember that? We had another theorem that said that limit as x approaches a of x exists and equals a. Right? Remember what that was called? Identity. Okay, that was the identity. ID, we called it ID. So here's how we do it. When we use a theorem or a rule as we go, and we're not using epsilon delta, we're just going to go ahead and show it with the equal sign. So you can show your steps. You can prove it along the way, right? And we got 2 to the 10th power. First, what is 2 to the 10th power? 1024. Just real quick in my head. Isn't it? Nobody has a calculator. 2 to the 5th. What's 2 to the 5th? What's 2 cubed? 8. 2 to the 4th is 16. 2 to the 5th is 32. You can keep going or just take 32 squared. You get 1024. Okay. Okay. 1024. All right. So a nice example there, right? So we had limit of the exponent is the exponent of the limit. Here's another one, very similar to that. This is where n is an integer. Well, really, n could be any real number. Of course, if it's 0, that becomes identity. Anything to the 0 power is 1, right? So anyway, so it really works for any real number exponent. So we have another one. If I have the limit as x approaches a of the nth root of f of x, well, very similar. This is going to be the nth root of the limit as x approaches a of f of x. Excuse me, f of x, which is going to be the nth root of L. Okay, so if we have the limit as x approaches a of f of x exists and equals L, we're going to have the nth root of L if it exists, if you can do it. I can't take the even root of a negative number though, right? I can't take the square root of -4. So if it exists. So let's just look at an example of this one. If I have the limit as x approaches 2 of the fifth root of, well, let me approach 32. Fifth root of x, okay? What's that going to equal? That's going to be the fifth root of the limit as x approaches 32 of x, right? How do I know that? So what theorem are we going to call this? Here we had limit of the exponent is the exponent of the limit. What do you think I'm going to do here? Limit of the root is the root of the limit. Could do that. Limit of the root is the root of the limit. So those are easy sound bites for remembering this stuff. And of course, what's this? This is going to be the fifth root of what? Why? Right. What law is that right here? The identity. So I can just put ID right there. Anyway, fifth root of 32, which is what? You all should know this one now. 2. Because 2 to the fifth is 32, right? Yeah. See how easy this game is? All right. So anyway, limit of the root is the root of the limit. So we have that as well. And really, I could have had a fractional exponent. So the nth root, how could I rewrite this? The nth root, instead of writing it like that, I could have, if I really wanted to, write this as the limit as x approaches a of f of x to the 1 over n power, right? Or I could rewrite this as f of x to the 1 over n power, right? So the nth root is the 1 over n power. So really, these are the same. It's just we think about them different when we see them written differently, right? All good with that? Trying to see if there's any others. Let's just do a quick example using limit theorem. So as you can see, life gets a lot better because of epsilon delta. All of these theorems exist because of the epsilon delta proofs. Like epsilon delta would prove these limits, okay? So that's why we spent time on the epsilon delta. But obviously the application of limits is a lot quicker and easier utilizing these limit theorems. So life's starting to get easier for us. So sometimes you go through the grind, go through 2-a-days, 3-a-days for volleyball. Some volleyball teams do 3-a-days, right? That's kind of a grind going through that stuff. And then all of a sudden you start getting better. It's good. Same deal in calculus. All right, so anyway, let's look at an example quick. What if I have the limit as x approaches try and do an easy one. Limit as x approaches 1 of the cubed root of, what do I got? Where'd it go? 2x plus 25. All right, so we want this limit, right? So what's the first thing I can do? Yep, so limit of the root is the root of the limit, so I can do that. Limit of the root is the root of the limit. So this says this is going to equal to the cubed root of the limit as x approaches 1 of 2x plus 25, right? Now, I know what we said before. We proved the limit of a line you could just plug in, right? And that's because we could say that the limit of the sum is the sum of the limit of the product is the product of the limit, right? So we can do that. But we also proved that the limit as x approaches a of mx plus b is ma plus b, didn't we? Okay, so anyway, what's this equal? Cubed root of what? 27. Because it's a line. So the line theorem, we can just write line if you want. Otherwise, you could step that out. Limit of the sum is the sum of the limit of the product is the product of the limit, and be 2 times 1 plus 25. Well, what is a cubed root of 27? 3, right? 3 cubed is 27. So we have that. Okay. So what I'm going to want you to do, so on the evens that you turn in, I want you to like show me the steps along the way. Don't just get the answer and plug in. Eventually, once we get past kind of your major half test that's coming up at the end of section 1.7, we're in 1.5. Then I'll let you just say, hey, if it's a polynomial, we can just plug in. Because polynomials we can plug in, but we got to get to that point. But we're not there yet, so I want you to show steps along the way. So, like I said, if you really wanted to, we could say, hey, limit of the sum is the sum of the limit. Limit of the product is the product of the limit. I'd let you do that here, and it'd be, you know, cube root of 2 times 1 plus 25. By the way, how does limit as x approaches 1 of 25, how we get that? Limit of a constant is a constant, right? Did I use k? I use k for constant. The book uses a c. Limit of constant is a constant, right? So really, when we use this line thing, really there were 3 different limit theorems going into that, although we proved it just in general with mx plus b, right? So I will let you use that. I haven't always. So getting easier. All right, let's just look at section 1.5. You may have already done this one, number 23. All right, so this is an odd exercise in the book. Odd exercises are great to see if you're kind of following along. What we have is the limit as x approaches 4 of the cubed root of a quotient, x squared minus 3x plus 4 over 2x squared minus x minus 1. As long as I wrote it down correct, I think this is what it is. Okay, so now I got the limit as x approaches a specific value of the cubed root of a quotient. So how can I use my limit theorems? So once again, trying to use epsilon delta, this could be pretty nightmarish, right? Kind of like getting up for early morning calculus when you don't have other classes, right? Yeah, kind of nightmarish. No one would want to do that. So anyway, what do I do first? Somebody from this side of the room, like you guys here today, you people. What's the first limit theorem I should use? Like somebody from this side.
Limit of the root.
Limit of the root is the root of the limit. Can I do that? By the way, you said root. I say root. That's because I grew up south I-80. I'm a hillbilly. Yeah, I don't know which one it is. Anyway, limit of the root is the root limit. So I can say this is the cubed root. The limit as x approaches 3 of x squared minus 3x plus 4 all over 2x squared minus x minus 1. Okay, so we got that. Now what? I still need parentheses around that too, kind of, I guess. Anyway, so limit of the root is the root limit. All right, somebody from the other side of the room, maybe the back row. Still with me back there? How could I split this one up? What's your best guess? Limit of the what? How you want to split it?
Not sure.
It's okay, nobody is. That's why I'm asking. Want to ask for help or take a shot? Just take a shot. It's free day. Take a shot. You miss, but you don't know anything. What do you think the easiest way to split that up and make it better is? What kind of problem is that overall? You got something on top, something on the bottom. It's division. So which one do you think we should use? Limit of the quotient is the quotient of the limit. Good. All right, so this is going to be the cube root of what? So the limit of this quotient, I can put the limit on top. So limit as x approaches 3 of x squared minus 3x plus 4 over the limit as x approaches 3 of 2x squared minus x minus 1. Does that make sense? Everybody good with that? Limit of the quotient is the quotient of the limit. Quotient of the limits. Sorry. Quotient of the limits. So basically, instead of taking the limit of the division problem, I can take the limit of the numerator over the limit of the denominator. All good with that? Now, what is this going to equal? How can I make that better? I'll give you a hint. We know how to deal with lines, right? The minus 3x plus 4 and the minus x minus 1, those are lines, aren't they? But then what do I got in front of them? I got an x squared, right? And I could add that line, 2x squared plus the opposite. So this is a line. This is a line. You could use the line theorem on those, but what do I have before I can get to that part? What am I doing with x squared in that line part? I should write this as add the opposite. So what am I doing with those line parts? Adding them. And what's addition? Sum. So could I say limit of the sum is the sum of the limits? Could I do that? Okay. So this becomes on top. Now this is where, and I know the first few times stepping through, this is why I make you write it out on the homework to turn in until eventually we'll just say, hey, it's a polynomial, plug it in. Right? This is a really nice function on top, really nice function on the bottom. Eventually we'll just plug 3 in and get an answer on top and on bottom, okay? But we're not there yet. We got to show the limit theorems for a while, okay? So limit of the sum on top, how do I write that? So that'd be the limit as x approaches 3 of what? What's the first part of that sum? X squared, and then plus the limit as x approaches 3 of what's left, which is the line, right? Wouldn't it be minus 3x plus 4? Everybody agree? And once again, in past classes, I would just make students write every single step, and I'd have all 3 sums. I'd say the limit as x approaches 3 of x squared plus the limit as x approaches minus 3 of minus 3x plus the limit as x approaches 3 of 4. But I'm changing my mind for your class, I guess. All right, so limit of the sum is the sum of the limits. So here's the first part of that sum, here's the second part of that sum. And then on the bottom, what do I got then? Limit, but it's limit first, right? Limit as x approaches 3 of 2x squared, and then plus the limit as x approaches 3 of what? Minus x minus 1. Everybody agree? And so once again, here's my 2 parts here. All good? So I'm splitting it up. And then now what can I do? Well, I can do a couple things. Once again, if you have 4-color clicky pen, right? The cool one that Noah's got. What can I say here? What does this equal? Do I know what this one is? So how'd you get it? You just plugged in 3, right? So negative 3 times 3 is negative 9 plus 4 is negative 5. So that part's negative 5. Why? Because it's a line, so we can just plug in. And what about this one? Plug in minus 3, and we get, what's minus 3 minus 1? You spend $3, and you spend another $1. You spent $4. So it's minus 4, and that's because it's a line, right? So you could either write line and rewrite it that way, or you could just do it like this. So this becomes the cubed root of the limit as x approaches 3 of x squared. And then what? Minus 5, right? So that's the first thing, then minus 5. And on the bottom, what do I got? Limit as x approaches 3 of 2x squared. That's the first one. And then minus 4, right? Because of lines. So I was just able to plug in, right? So it's making it, so we're getting closer. And then now what do I do with the first part? So what's this top one? What can I say? What kind of problem is that? Limit of the exponent is the exponent of the limit. Okay, and then what? So I could rewrite that as limit as x approaches 3 of x quantity squared. And then as x approaches 3 of x, what's that? Do I need to do 2 steps? I mean, I do, right? I'm also using the identity here, right? So limit as x approaches 3. So if I rewrite it as limit as x approaches 3 of x quantity squared, then I use the identity for that part, right? And as x approaches 3, what's x approach? 3. So it's 3 squared, right? So the limit of the exponent is the exponent of the limit, and then the identity. All good with that? Okay. And then we still have our minus 5. It's still there, right? So that's the top one. What do I got on the bottom? I've got 2x squared. So what can I say there? 2x squared. So what kind of problem is that? It's not 2x quantity squared, it's 2 times x squared. What are you doing with the 2 and the x squared? Multiplying. So limit of the product is the product of the limit, right? So I'm gonna go under here. So I'm gonna say this is the limit as x approaches 3 of 2 times the limit as x approaches 3 of x squared. And this is limit of the product is the product of the limit. You okay with that? All okay with that? You can stand up if you need to. Sorry. I know I'm a little low there. And we come back up top.
It's okay.
All right, and then what? What's this one? Limit as x approaches 3 of 2. What is that? It's a constant. So this is 2 because I've got limit of a constant is a constant. As x approaches 3, 2 approaches 2. A height of 2 stays at a height of 2, right? Doesn't matter that x approaches 3. So that's 2. And then I've got the limit as x approaches 3 of x squared. What can I do with this one? Same thing I did right here, right? We already have it. It's 3 squared, right? So it's 2 times 3 squared, and that's because I've got limit of the exponent is the exponent of the limit, and limit of the identity. So for this one, that equals times 3 squared, right? All good with that? And then I still have my minus 4, don't I? All right. Now, long story short, what's that equal? So that equals, what's this limit equal? The cubed root of 3 squared minus 5 is 9 minus 5 all over 2 times 3 squared is 2 times 9, which is 18 minus 4. So this is the cubed root of 4/14, which reduces to the cubed root of 2/7, if I did it right. I don't think I did it right, but Oh, wait a minute. It was x approaches 4. Who plugged in a 3?
You wrote on.
Okay. I'm going to go back live, and I'm going to put like number 23, and I'm going to change this from x approaches 4. Like, how come no one told me that? X approaches 3. Everything else is correct, so it's a cube root of 2 7s. Now you can go do number 23, which approaches 4, and it ends up being a nicer answer. But anyway, it's the same process. Isn't that great? So you still get to do number 23 and look at the answers in the back of the book and verify that you know how to do it. All right, but basically what I'm doing is I'm doing steps along the way. Now, won't life be so much easier after your half test? And you can just say, hey, limit of the quotient limits, and then I can just say poly, plug it in. Life will be great later when you're older. Is that what your parents keep telling you? Like when you're older, life's easy? No, life gets hard when you get older. But for you, I'm going to make it easy. You're welcome, no charge. That's also free. Well, you might be paying for this, but I don't think so. All right. Speaking of paying for this, like if you went to UNI or Creighton and paid for this, you know how much this course would cost? Any idea? What's the cost to go? So we were talking about Iowa. What's the cost to go to the University of Iowa? Has anybody looked there, going to school there? Anybody know anybody going to school there? Iowa, Iowa State, UNI. It's about 20 grand a year. About 10 grand a semester. This would be about a third or so of your load. Be about 3 grand. At least 2 grand, but 2 to 3 grand. That I'm saving you because you're doing calc today. All right. Any questions on this? All good? All right. Do you want any more examples, or do you think you're okay? Couple more. Let's look at a couple more. Let's look at number 31. All right. But anyway, this using these theorems definitely a lot easier than trying to come up with for any epsilon there exists a delta argument, right? For sure. All right, but all of those theorems were proven using epsilon delta. Okay. This is number 31 in the book. How about I do one like number 31? So let's stick with the theme that allows you to do number 31. And I'm going to take the limit as x approaches 5 of x squared minus 25 over x plus x minus 5. How about we do that? Okay. First of all, here's my function. What is if this is f of x, what is the domain of f? What's the domain? Because I need to be defined on some open interval containing 5 except possibly 5 itself. What values of x can I plug in here? All of them except what? Except the set containing 5, right? So for you interval fans, minus infinity to 5, union 5 to infinity, right? So I'm defined on some open interval containing 5 except possibly 5 itself. I could go 0 to 10. 0 to 10 is an open interval containing 5. 5's in there, but I'm not defined at 5, which is fine. Okay, so I can use limit theorems here. And then what are we going to do? What kind of problem is that? I'd say that's one, Connor, but we had one back there. Should we do a cheer live on video? Next one, I'm going to do a cheer live on video. All right. For those of you watching, tape delay. Crazy. All right, anyway. Can't even say tape delayed anymore. It's not tape, is it? DVR delayed. How do you say that? Like, how do you say tape delayed? What's today's word for that? Anyway, what are we gonna do here? What theorems? What rules? What proven facts? Daniel, you got something for me? Well, what kind of problem is that? It does, but before, basically, I'd let your eyes see that as something on top over something on the bottom first. So that'd be a quotient, right? Okay, so what if I did that? Limit of the quotient is the quotient of limit. Okay, so it'll be limit as x approaches 5 of the top, x squared minus 25, over the limit as x approaches 5 of x minus 5, right? Now, I'm gonna, these are polys, but what would you get here if you step out the theorems? Knowing that I said, well, you can cheat a little bit if it's polynomial, knowing that eventually we're just gonna be able to say poly and plug it in. But you get on top 0. So this is gonna end up being 0 over what? What do you get on the bottom? 0. So 0 over 0 is a problem for limits. Because what's 0 over 0? We talked about this before. Nope. Indeterminate. It's indeterminate. You can't determine the answer unless you have more information. Well, we're going to have more information here. So what I'm going to do to solve this, so this is an unknown quantity. It could be 0, it could be 89, it could be 5, it could be does not exist, it could be infinity. Okay, we don't know what do you want me to say, Kobe? It could be 10. Could be 11. Okay. Anyway, so what am I going to do? How do I do it now? I got to manipulate. So when you have 0 over 0 forms, we need to manipulate, right? To find the limit. This is what Khan Academy, so I know I got a question. Do we really have to watch all those videos? Not if you know how to do everything. You don't have to watch them all, but you do have to do all the Khan assignments, but those videos really help you with problems like this. So what can I do here? How can I manipulate this? We already did this. This is the limit as x approaches 5 of what? We did this back in section 1.1, I believe. We're going to manipulate by factoring, aren't we? So this is x plus 5 times x minus 5 all over x minus 5. Difference of 2 squares, right? And then what can I do? Can I cancel these out? And what do those cancel to? 1s, as long as x doesn't equal what? So this equals 1 if x doesn't equal 5. Does it? No, I'm taking the limit as x approaches 5. So you can get as close as you want from either side, but you can't touch it. So 5.000001 or 4.9999999 is fine. 5, not okay. So this is equivalent to what? The limit as x approaches 5 of x plus 5, where? On the domain of f. Do you remember doing that back in section 1.1? That's why we did problems like that you're like, why are we there? I'm never going to use this in my life again. Yeah, you are. Section 1.5. Anyway, and what's this equal? Logan? What's this limit equal? Limit as x approaches 5 of x plus 5. X is 5. What's x plus 5?
10.
Yeah, this is just 5 plus 5, which is 10, right? All right, why? What's your theorem? What theorem did you use? You could say line, or you could say limit of the sums, the sum of the limits, and then the identity and limit of a constant is a constant. I don't care which one you do, okay? But obviously it's easier to say line, right? Instead of 3 reasons, it's 1 reason. So it's a line we can just plug in. So you see what we're doing? X approaches 5, so I'm okay. As long as you can plug in, it's okay, right? Which for lines it is. For polynomials, it's going to be, right? But you just can't do it for a poly yet. I'm making you step it out for a bit and show all the reasons. Anyway, that equals 10, right? So if I were to graph this thing, so we did this before too, but I'm going to revisit how we did it. If I'm going to graph f of x equals x squared minus 25 all over x minus 5. What does this look like? This is equivalent to x plus 5 on the domain of f, which is all reals excluding the set containing 5, right? So over at 5 and up at 10, I have a what? I have a hole, and 0, 5 is on my graph, right? That's my y-intercept there, but I have a hole at 5, 10. Because I would have hit a height of 10. So 10 is my limit, but I'm not defined there. I'm not defined at x equals 5, right? So the limit, L is 10, A was 5, right? We can do epsilon delta arguments here if you want, which you should know how to do. This is equivalent to a line away from the hole, right? Away from x equals 5, it's a line. So it's a line with a hole in it, right? But you could actually go back with epsilon delta arguments if you really wanted to and say, hey, let epsilon be any tiny number greater than 0. Come back, right? I think I was using blue there, but anyway, and then find a delta, right? And delta in this case, setting delta equals to epsilon will work because it's equivalent to the line x plus 5, epsilon divided by the absolute value of the slope is epsilon divided by 1, which is epsilon. All right. Or delta, I don't know. Delta equals epsilon over 1, which is epsilon. All right, good with that? So what do we notice? So when we can use theorems, use theorems. When we need to manipulate, let's manipulate. Let's look at another one. Let's do one like number 43. Once again, lots of con videos that go along with ones like these. So if you get one that like, I really don't know how to handle this one, you know, we got to try and manipulate it. So let's look at an example. The limit as h goes to 0 of the square root of h plus 5 minus square root of 5 all over h. Okay, well, what can I do here? I can say limit of the quotient is the quotient limit, and then I can say the limit of the difference is the difference of the limit on top. Then I could say limit of the root is the root of the limit, right? I could do that stuff, but what am I going to get? When you do all that stuff, what do you get? If I plug in 0 right here, what am I getting? Square root of 5, right? And then line, right? Limit of the root is the root of the limit, and then line, or limit of the constant is a constant. So I have all these reasons here. This would be your using your theorem stuff. Limit of constant is a constant, right? But anyway, square root of 5 minus square root of 5 all over what? 0. And what's the bottom reason that that's 0? If we started with limit of the quotient as a quotient limit. Limit as h approaches 0 of h is 0. Why? Okay.
What?
And I can tell when you don't want to answer. Limit as h approaches 0 of h is 0. Why?
Because h is approaching 0.
Right. And what theorem is that?
Oh, identity.
Identity. Thank you. All right. So it's not hard. It's a duh thing, right? But anyway, and what's this equivalent to? What's this equal to? 0 over 0. Is that a problem? 0 over 0 is a problem. It's indeterminate, right? So we need to do some algebraic manipulation. Well, what did we do last time? We factored, didn't we? Can't factor here, Carter. That's a problem. Now what? I don't know how to factor that. It doesn't factor. Anybody got an idea? Anybody watch ahead on the videos? This is a fraction, right? It's top over bottom. What can you do to fractions? Legally, mathematically equivalent. Multiply top and bottom by the same thing, right? Or divide top and bottom by the same thing as long as it's not equal to 0. So I do need to multiply top and bottom by the same thing. So this is equivalent to the limit as h approaches 0 of the square root of h plus 5 minus the square root of 5 all over h, and then times, I'm going to multiply it by something. Okay, so this is, if you think of this as a minus b, that's a binomial, right? A minus b. If you think of the top one as something minus something, it's like a minus b or x minus y. It's just a polynomial, right? Or a binomial. If you think of it, it's not a polynomial because it's got a square root in it. But it's a binomial. It's a two-term polynomial, even though it's not a polynomial. But it's like that, right? So if I've got a plus b, I could multiply it times a minus b. So I'm going to multiply by the conjugate of that thing. So I'm going to multiply top and bottom by the conjugate. What's the conjugate of a plus b is a minus b. What's the conjugate of a minus b? It's a plus b, right? It's the same thing, opposite sign in the middle. So that's called a conjugate. I know you learned that in like algebra, right? Probably even algebra 1. But anyway, so I'm going to multiply this times. By the way, the first term doesn't change. The second term doesn't change. So you're not putting a minus sign inside this h plus 5. That stays h plus 5. Does that make sense? The only thing you're changing is the sign in between. So this is going to be a plus square root of 5. Now, what I did to the top, I got to do to the bottom. So this is square root of h plus 5, and then plus square root of 5. So I multiplied top and bottom by the same thing. By the way, is this going to equal 0? Close to 0? No, it's going to be square root of 5 plus square root of 5 over square root of 5 plus square root of 5, which is 2 square root of 5 over 2 square root of 5, which is it's close to 1. Well, it's exactly equal to 1, actually, no matter what h you plug in. The only h we can't plug in is negative 5. Is that anywhere near 0? I can plug in negative 5. I just can't plug in bigger than negative 5, like negative 6. Then I'd be taking square root of negative numbers. So I can't plug in less than negative 5. But anyway, so I'm good here, right? All good with that? What happens if I multiply this out on top? What happens if I multiply this out? What do I get? How do you multiply that out? First times first, right? So this is going to be equivalent to the limit as h approaches 0 of what's square root of a times square root of a? Anyone? Anyone? Trevor? A? Yeah. All right. Getting ready for, we'll do the cheer off video as soon as we're done. All right, but anyway, so this is h plus 5, right? Because square root of h plus 5 times square root of h plus 5 is h plus 5. And then what happens to the outer and inner terms? So it's square root of 5 times the square root of h plus 5 minus the square root of 5 times square root of h plus 5. That goes away, right? The outer and the inner cancel. And then last times last. Minus times plus is minus. And then square root of 5 times square root of 5 is 5. And then all over, what? Do not multiply the bottom together. Do not multiply it. Leave it factored. Square root of h plus 5 plus square root of 5. All right, got this. What happens on top now? What happens on top? These 5s cancel. I get h. I'm left with an h on top over h times that red thing. What happens to the h's now? These cancel to 1s as long as it's not 0 over 0, and it's not, because h can get as close as it wants to 0 without touching it. Okay, so this is equivalent to 1 over, the limit as h approaches 0 of 1 over square root of h plus 5 plus square root of 5, right? And now what can I do? I can let h go to 0. I can say a limit of the quotient is a quotient of limit, etc. All that stuff that I set up here, I can do here now. And I get 1 over, if I plug in 0, I get square root of 5 plus square root of 5, which is 1 over 2 square root of 5. Everybody agree? It's not going to be the answer in the back of the book because they're going to rationalize the denominator and make that square root of 5 over 10. So this is equivalent to the square root of 5 over 10 as long as you match. You do not have to rationalize the denominator. The only reason that we ever rationalize the denominator is to find a limit, just so you know. I rationalized the numerator here, and that helped me find a limit. So I rationalized the numerator by multiplying top and bottom by conjugate. So there's a lot of tricks like that. I know I kept you a little long. I appreciate your patience. Thank you so much. Section 1.5. Watch those comm videos, help you with some other examples. Ready break.